Have you ever stopped to think about something like a modern computer chip? I mean, billions of transistors. How do engineers even describe that, let alone design it so it works, all before it's, physically built?
It's a massive undertaking, really is. And that's precisely where hardware description languages, HDLs, come into play. They are essentially the blueprint languages for all this digital stuff.
Right. And that's what this deep dive is all about. We want to pull back the curtain on these sort of unsung heroes, Verilog, VHDL, and the big one, System Verilog. We'll dig into where they came from, what they can do, and how they've changed to handle today's, frankly, staggering chip complexity. Think low power, think verification.
Yeah, the whole gamut.
Our goal is really to give you a shortcut, a way to grasp these foundational tools that, shape pretty much everything digital around us.
Absolutely. And for this, we've drawn on quite a bit of research looking into the core ideas behind each language, the methodologies, how they're actually used today, and, cutting edge hardware development. It's a pretty deep look.
Okay, let's dive in. Section 1. The historical battleground, maybe. Verilog versus VHDL. Let's start with Verilog. Mid-'80s, right? And engineers needed something practical.
Exactly. Verilog popped up, really built for pragmatism, get stuff done fast. And crucially, it had this C-like syntax. The idea was if you knew C, you could pick up Verilog relatively easily. Rapid prototyping was the name of the game.
But that C-like feel
sounds
like it could be a trap.
Oh, it was a very common one. Because it felt like C engineers, especially coming from software, tended to write it sequentially, like a program.
Okay.
And that code might simulate perfectly fine, but then you try to synthesize it, turn it into actual hardware gates, and disaster. Inefficient, maybe completely wrong. It really hammered home that fundamental difference.
You're describing parallel hardware, not writing sequential software steps.
Right. Parallel versus sequential. Huge difference. So if you're listening and have a software background, you can probably see how easy it'd be to make that mistake.
I'm feeling it.
So Verilog was the pragmatist. Meanwhile, VHDL comes along from a totally different angle, completely different. VHDL was born out of a U.S. Department of Defense mandate, and it was heavily influenced by Ada, a language designed for super high reliability software.
Ada. Okay, so reliability is key here.
Absolutely. VHDL was built for rigor, for being absolutely unambiguously clear. Precision was paramount.
That sounds wordy.
It is. VHDL is famously verbose. That's often seen as a downside. But, from its original design goals, that verbosity, it's actually a feature.
A feature? How so?
It forces you to be explicit. Strict type matching, clear declarations for everything. It catches potential errors right at compile time.
Instead of finding them later in simulation.
Or worse, when the chip is actually made on silicon. That's why VHDL is still dominant in places like aerospace, defense, mission critical stuff.
You absolutely want that safety net there.
No question. Compile time checks are gold in those fields.
Okay, so for years you had this dynamic. Verilog speed versus VHDL's rigor.
Yeah.
But then chip complexity just
exploded, right? It really did. Exponential growth. We hit a point maybe late 90s, early 2000s, where verifying the design, proving it worked, started taking more time, more effort than actually designing it in the first place.
Wow. The verification crisis.
That's what they called it. Because the traditional ways, writing test benches in basic Verilog or VHDL, they just couldn't keep up. They weren't powerful enough for the scale of the problem.
That sounds like a serious bottleneck.
It was critical. You had designers creating these incredibly complex chips, but the tools and methods to guarantee they were correct, they were lagging behind badly.
So something had to change. Enter System Verilog.
Exactly. And System Verilog wasn't just, Verilog plus Platoon. It was a monumental leap. Its primary goal was to tackle that verification crisis head-on by bringing design and verification closer together.
How did it do that? Twofold approach, wasn't it?
Pretty much. First, it enhanced the design language itself. It pulled in a lot of features that VHDL users liked, things like enumerated types, structures, interfaces, making the design description richer, more robust.
Okay, so borrowing good ideas.
And cleaning up some old Verilog quirks, too, like replacing the often confusing reg keyword with a clearer logic type, and adding specialized always blocks, always start for flip-flops, always come for combinational logic, always slash for latches. That helped prevent those nasty simulation synthesis mismatches we talked about.
Right, making the intent clearer for the tools.
Yeah.
But the big revolution was on the verification side.
Oh, absolutely. That was the game changer. System Verilog essentially built a world-class dedicated verification language right on top of the hardware description part. It integrated powerful concepts, drawing heavily from object-oriented programming, or OOP, and other specialized verification languages.
OOP and hardware verification, how does that work?
Think about building reusable, intelligent test components.
Oh.
With OOP, you get classes, objects, properties, methods, just like in software. This lets you model things dynamically. For instance, you could create a basic packet class.
Okay.
This class describes a generic data packet. It might have properties like data, address, kind, maybe even a method to print itself out. These properties can be randomized.
Randomized.
We'll get to that. But the beauty of OOP here is inheritance and polymorphism. You can take that basic packet and extend it. Create specialized types like Ethernet packet or PCI packet that inherit the basic stuff but add their own specifics.
Ah, so you build up complexity modularly.
Precisely. And polymorphism, using virtual methods, lets you write generic test code that can handle any of these packet types without knowing the exact type beforehand. This is fundamental to how modern verification libraries like UVM work.
You mentioned randomization. How does that help find bugs?
That leads us to constrained random verification, or CRV. This is huge. Instead of a poor engineer trying to dream up every single possible test case manually, which is impossible for complex chips.
Right, there'd be millions.
Billions, maybe. With CRV, you define the rules. Constraints. You tell the tool, generate random stimulus, but make sure it follows these rules. Maybe the packet length must be between 64 and 1500 bytes, or the address should be in this specific range.
So you guide the randomness.
Exactly. You let the tool explore the state space randomly within the legal boundaries you define. This is incredibly powerful for hitting weird corner cases. Those combinations of inputs that you'd never think to test by hand, but which might just break the design.
Like generating a tiny packet immediately followed by a giant one, or hitting a specific address pattern.
All those tricky scenarios. You can randomize that Ethernet packet we mentioned, let the tool pick valid sizes and addresses, and then maybe for one specific test, you add an inline constraint. Okay, now just give me a packet smaller than 100 bytes, or make sure this one goes to this specific destination. It gives you both broad exploration and fine control.
Okay, so you're throwing all this random constrained data at the chip. How do you know if you've actually tested what you intended to test? Have you covered all the important functionality?
Excellent question. That's where functional coverage comes in. It's different from traditional code coverage. Code coverage just tells you, did this line of RTL code execute?
Which is useful.
But it doesn't tell you if you actually tested the intended behavior. Functional coverage lets you define specific scenarios or conditions you want to see happen during simulation. Did we send all the different types of packets? Did we get transactions targeting high, medium, and low address ranges? Did we see a write followed immediately by a read to the same address?
So you define coverage goals.
Right. System Verilog has constructs like cover group, cover point, and cross to define these functional coverage points. You might put a cover group inside a monitor component, for example, to track combinations of transaction types, read-write, and address ranges. Then during simulation, the tool tracks which of these coverage points have been hit.
And you run simulations until your coverage goals are met.
Ideally, yes. It gives you a metric, a degree of confidence that you've actually exercised the important parts of the design's functionality.
Okay, OOP, CRV, functional coverage.
Yeah.
What about assertions? SVA.
System Verilog assertions, SVA. Another cornerstone. Think of SVA as a way to describe behavior over time. It's a temporal language. You can write properties that specify things that must happen or things that must never happen according to your design's specification or a protocol.
Like protocol rules.
Exactly. For example, you could write an assertion that says, whenever a request signal goes high, an acknowledge signal must go high within 1 to 5 clock cycles. Or, the grant signal must remain stable as long as the enable signal is low.
So you're embedding checkers directly into the design or test bench.
You are. These assertions are checked continuously during simulation. If one fails, you get an error pinpointing exactly when and where the unexpected behavior occurred. And importantly, these same SVA properties can often be used by formal verification tools too.
We'll get to formal verification later, but putting all these System Verilog verification features together, OOP, CRV, coverage, SVA, what does that enable?
It enables the creation of sophisticated, reusable, and standardized verification environments. And the culmination of all this is the Universal Verification Methodology, or UVM.
UVM, that's the big industry standard now, right?
It absolutely is. UVM is basically an open source library written in System Verilog that provides a standard structure, a methodology for building these complex test benches. Think of it like a highly organized factory for testing chips.
A factory. Okay, explain.
A UVM test bench has standard components. You have the test top, which connects your design, the DUT, to the test bench. You have a specific test class that configures the whole environment for a particular scenario. Inside the environment, you usually have agents for each interface of your DUT.
Agents.
An agent typically contains a sequencer, which manages streams of test data called sequence items or transactions.
Like those packets we talked about.
Exactly. These transactions are generated by sequences. The sequencer feeds them to a driver, which takes the transaction level data and translates it into the actual pin wiggles, the signal changes, on the DUT's interface.
So it drives the inputs.
Right. Then a monitor observes the DUT's pins, captures the activity, and translates it back into transactions. And often you'll have a scoreboard component that compares the transactions captured by the monitor against expected results, maybe from a reference model.
Wow, okay. That sounds very structured.
It is, and that structure, that modularity, is the key. It allows for massive reuse. You can reuse agents, sequences, scoreboard components across different projects or different tests within the same project. It makes verification scalable and much more manageable for these huge, complex designs.
So System Verilog and UVM really dominate the verification space for complex chips. But what about VHDL? Did it just fade away?
Not at all. While System Verilog clearly won the verification battle, VHDL remains a very strong contender, especially for RTL design itself. Its rigor is still highly valued, particularly in FPGA development and those high reliability sectors we mentioned earlier, aerospace, medical, automotive.
So it still has its strengths in design. What are some key VHDL features for that?
Well, it has powerful constructs for describing regular structures. Generate statements are a good example. You have for-generate, which is great for creating arrays of things. Think building an endit register by generating n instances of a single flip-flop component.
Okay, makes sense for repetitive structures.
And then there's if-generate, which lets you conditionally include hardware. Maybe you only want certain debug logic included if a specific parameter is set, or you want to select between different interface components based on configuration.
What about making designs flexible, reusable, like parameters in Verilog?
VHDL uses generics for that. They work similarly to parameters, letting you create highly configurable IP blocks. You can write one piece of VHDL code for, say, an adder subtractor, and use generics to set the data width. So that single source file can actually describe a whole family of adders.
So generics for parameterization. Anything else notable?
VHDL also has packages. These are fundamental for code organization and reuse. You can group together common declarations, types, constants, functions, procedures into a package, and then just use that package in different parts of your design. It promotes good software engineering practices applied to hardware.
What about those shared variables you mentioned earlier?
Yes, shared variables and protected types. Those came in VHDL 2002, primarily aimed at improving VHDL's capabilities for verification test benches. They provide a way for different processes in a simulation to communicate safely, ensuring only one process can access shared data at a time. It was sort of VHDL's answer to some of the concurrency challenges that OOP helps solve in System Verilog test benches. But crucially, remember, shared variables are not synthesizable. They don't represent hardware. They're for simulation modeling.
Okay, so VHDL is still very much alive for design, especially where rigor is key. Now, let's shift gears up the abstraction ladder again. We talked about RTL design. What about describing things even more abstractly, like using C++, high-level synthesis, HLS?
HLS, yes. This is a really interesting area. The fundamental idea is, what if you could write your algorithm, maybe signal processing, image processing, complex math in a high-level language like C, C++R, or System C, and have a tool automatically generate the RTL hardware for you?
That sounds incredibly appealing, especially for algorithm folks who aren't necessarily RTL experts.
It is. The promise is huge. It can bridge the gap between algorithm developers and hardware engineers. Productivity can go way up because you can design, test, and iterate on your algorithm much faster at the C level. The HLS tool then handles the complex process of figuring out the scheduling of operations. binding them to hardware resources like adders and multipliers, and generating all the control logic.
Faster iteration sounds great. What are the downsides? Is it magic?
Definitely not magic. While HLS offers big productivity gains, faster verification at the C level, and lets you explore different hardware implementations quickly just by changing compiler directives called pragmas.
Pragma.
Yeah, they're like hints to the HLS compiler. You might add a pragma to tell it to pipeline this loop or unroll that loop to create parallel hardware. But the downsides are real. You often lose fine-grained control over the exact hardware structure produced. Debugging the generated RTL can be quite challenging. It's often not pretty, human-readable code.
Ah, so you might not understand the hardware it creates.
It can be tough, yeah. And importantly, getting good results efficient, high-performance hardware from HLS isn't automatic. You can't just throw any old C++ code at it. You need to write code in a hardware-aware style.
Hardware-aware C++. What does that mean?
It means you have to think about the underlying hardware implications of your C code. For example, you absolutely must avoid things that don't map well to hardware, like dynamic memory allocation, malloc, new. You need to use specific data types, often provided by the HLS tool vendor like Apint or Accent, which let you specify the exact bit width you need for variables rather than just using standard int or float.
Because every bit costs area and power in hardware.
Exactly, and you need to explicitly manage parallelism using those pragmas we mentioned. Take a FIR filter algorithm, for example, often implemented as a loop. In C++, say it's just a sequential loop. To get high-performance hardware, you'd add pragmas, like hashtag pragma HLS pipeline tie 1 to tell the tool to make the loop execute with a new input every clock cycle. Or hashtag pragma HLS unroll to essentially duplicate the loop body's hardware, creating parallel multipliers and adders for maximum throughput. So it requires a different way of thinking when writing the C++ code.
Okay, so HLS is powerful, but requires careful coding. Let's talk about another critical constraint in modern chips, power. As things get smaller and faster, power consumption's a huge deal, right?
Absolutely massive. It's often a primary design constraint now, not an afterthought. We mainly worry about two types, dynamic power and static power.
Dynamic and static, what's the difference?
Dynamic power is consumed when signals switch, when transistors turn on and off. It's proportional to clock frequency, voltage squared, and the amount of switching activity. Static power, or leakage power, is power consumed even when the circuit isn't actively switching, just due to transistors leaking small amounts of current. As transistors get smaller, leakage becomes a bigger and bigger problem.
So how do designers tackle dynamic power?
The number one technique is clock gating. It's simple in concept. If a block of logic isn't doing anything useful in a particular clock cycle, just temporarily stop its clock signal. No clock, no switching, no dynamic power.
Seems straightforward. How do you implement it?
The safe way is to write your RTL using a clock enable style. You have your logic inside an if enable statement. When the enable signal is active, the logic updates. When it's inactive, it holds its state. Then you let the synthesis tool automatically infer a special pre-designed library cell called an integrated clock gating ICG cell.
Why use a special cell? Why not just any the clock with the enable signal?
That's dangerous. Manually gating a clock with a simple A and D gate can easily introduce glitches or timing problems on the clock signal itself, which can cause all sorts of functional failures. ICG cells are carefully designed to avoid these issues. So, rule number 1, infer clock gating, don't build it manually.
Okay, infer clock gating for dynamic power. What about static power, the leakage?
For leakage, the main technique is more aggressive. Power gating. Here, you actually cut off the power supply completely to blocks of the chip that are idle for longer periods.
Wow, completely off.
Yep. To do this, you need special power switch cells, which act like internal relays to turn the power on and off for a block, a power domain. You also need isolation cells at the boundaries between powered on and powered off domains to prevent invalid signals from propagating. And if you need the block to remember its state while powered off, you need state retention registers, which use a trickle of power to hold their value.
That sounds architecturally complex.
It is. And you need a dedicated power management unit, PMU, often a small processor, to control when blocks are powered up or down. Because this is so architectural, you don't typically describe power gating directly in your Verilog or VHDL.
How is it described then?
There's another technique first, related to power, multi-voltage design. You run different parts of the chip at different voltage levels. Maybe the high-speed core runs at a higher voltage, while less critical peripherals run at a lower voltage to save both dynamic and static power. This requires special level shifter cells whenever signals cross between these different voltage domains to adjust the signal levels correctly.
Okay, power gating, multi-voltage. How do the tools know about all this?
That's where the Unified Power Format, UPF, comes in. It's an IEE standard, 1801. UPF is essentially a separate file, a side file, that describes the power architecture of the chip. It defines the power domains, which supply nets power them, where the power switches are, where isolation and level shifters are needed, how state should be retained, and so on.
So the functional HDL describes what the logic does, and the UPF describes the power structure around it.
Exactly. It separates the concerns, which is quite elegant. The synthesis and place and route tools then read both the HDL and the UPF to implement the design correctly with the intended power-saving features.
Fascinating. Okay, another major challenge in big chips, multiple clocks. You mentioned integrating IP blocks. They often come with their own clocks, right?
Very often, yes. Modern system on chips, SoCs, are full of different blocks running on different clocks, often asynchronous to each other, meaning there's no fixed phase relationship between them. Dealing with signals crossing between these different clock domains is one of the trickiest and most critical parts of digital design.
Why is it so tricky? What can go wrong?
The biggest danger is metastability. When a signal generated by one clock domain is sampled by a flip-flop running on a different asynchronous clock, that sampling flip-flop can enter a weird, unstable state where its output isn't clearly a 0 or a 1. It might oscillate or take an unpredictably long time to settle.
An unstable state. That sounds bad.
It is. If that metastable signal feeds into other logic before it settles, it can cause functional failures. Maybe a short pulse on a control signal gets missed entirely, data loss. Or even worse, if you're sending multiple bits across the clock domain like a data bus, different bits might get captured at slightly different times due to this metastability resolving differently for each bit. This leads to data incoherency, where the receiving side captures complete garbage even if each individual bit eventually settled.
Yikes. So how on earth do you safely get signals from one clock domain to another?
We use specific design patterns called clock domain crossing or CDC techniques. The choice depends on the type of signal. For single-bit control signals that don't change too frequently, the standard solution is the 2-flop synchronizer, sometimes 3 flops for extra safety.
2-flop synchronizer. How does that work?
You basically pass the incoming signal through 2 or 3 flip-flops clocked by the destination clock domain, one after the other. The idea is that if the first flip-flop goes metastable when sampling the asynchronous input, it has a full clock cycle of the destination clock to resolve to a stable 0 or 1 before its output is captured by the second flip-flop.
Ah, you give it time to settle.
Exactly. And the crucial rule is you never use the output of that first synchronizer flop directly in your logic. You always use the output of the second or third flop, which should be stable.
Okay, that handles single bits.
Yeah.
What about multi-bit buses, like data or addresses? You said synchronizing each bit independently is bad.
Very bad. You'll get that data incoherency problem. For multi-bit buses, you need more robust methods. If the data changes infrequently, you can use a handshaking protocol. The sender raises a request, the receiver acknowledges, data is transferred, then the signals deassert. It's safe, but adds latency.
Okay, handshaking for slow data, faster data.
If the data bus is stable for multiple cycles of the destination clock, you can sometimes use a mux recirculation scheme. Here, you synchronize just a single enable or valid signal using a 2-flop synchronizer, and that synchronized signal is then used to control when the entire multi-bit bus is latched on the destination side. But this relies on the data being stable long enough.
And for high speed? Streaming data between domains.
The gold standard there is the asynchronous FIFO. FIFO stands for first in, first out buffer. It's essentially a small dual-port memory, one port connected to the write clock domain, the other to the read clock domain.
How does that solve the synchronization?
The clever part is how the FIFO manages its internal read and write pointers, which track how full or empty the memory is. To safely pass these pointer values between the clock domains, so the write side knows if it's full and the read side knows if it's empty, asynchronous FIFOs typically use gray code.
Gray code.
Gray code is a binary encoding scheme where consecutive values differ by only one single bit. Normal binary counting can have multiple bits changing simultaneously, like going from 3, which is 011, to 4, which is 103 bits flip. If you tried to synchronize a normal binary counter across clock domains, you could capture an intermediate invalid value due to metastability.
But with gray code.
With gray code, only one bit ever changes between adjacent pointer values. So even if that one bit goes metastable during synchronization, the worst that happens is you might temporarily read the previous pointer value or the next pointer value. You never read a completely nonsensical value. It effectively turns the multi-bit pointer synchronization problem into a much safer single-bit synchronization problem for each bit, which we know how to handle with two-flop synchronizers. That's why async FIFOs are so reliable for CDC.
That's really clever. Okay, so much careful design goes into handling these hardware realities, but stepping back a bit, it's crucial for anyone starting out to understand that not everything you write in an HDL file actually turns into hardware, right?
Yep.
Synthesizable versus non-synthesizable.
Absolutely fundamental concept. A lot of HDL constructs exist purely for simulation, for building test benches, or for controlling the simulator. They have no physical hardware equivalent.
Like what?
Obvious examples are things like explicit time delays, #10 in Verilog, or after 10s in VHDL. Those tell the simulator to wait, but you can't build a gate that just waits 10 nanoseconds. Also, initial blocks in Verilog, which define behavior only at the start of simulation. File input-output operations, FAW, fraud, etc. And simulation control tasks like display, monitor, finish, all purely for the simulation environment.
So the synthesis tool just ignores those.
Pretty much, yes. Or it will flag them as errors if you try to synthesize a module containing them. But there are more subtle pitfalls, too. Things that look like they might describe hardware but aren't synthesizable, or synthesize badly.
Such as?
Well, in classic Verilog, for loops generally need constant bounds to be synthesizable into parallel hardware. Using variables for loop bounds often doesn't work. The mixing of blocking and non-blocking assignments inside the same always block in Verilog is another big one. It can lead to code that simulates one way but synthesizes completely differently. That's a classic source of bugs.
The blocking confusion.
Yeah.
Heard about that one.
And another common trap, especially for beginners, is inferring latches unintentionally. If you write an if statement or a case statement inside a combinational always block, like always at or always comb, and you forget to assign a value to one of your outputs in every possible branch, the synthesis tool assumes you want the output to hold its previous value in those unassigned cases. To do that, it has to infer a latch, a memory element. If you intended purely combinational logic, that inferred latch is usually wrong, can cause timing problems, and can be really hard to track down. Good linters will usually warn you about this.
Linters. We'll get to those. Okay, so assuming you're writing synthesizable code, how do you decide whether to describe the behavior abstractly, like CU plus B, and let the tool figure out the adder, versus explicitly telling it, use this specific adder component from the library? Inference versus instantiation.
That's a great question, a common trade-off. Inference, where you write behavioral code and let the synthesis tool deduce the required hardware structures, like inferring an adder from plus C or flip-flops from always huff, is generally preferred for portability and readability. Your code describes the intent rather than a specific implementation.
So it's more flexible.
Yes, generally. But you are relying on the synthesis tool being smart enough to choose an efficient implementation. Instantiation, on the other hand, is where you explicitly call out a specific hardware component, often a technology-specific primitive from the FPGA vendor or ASIC library, like a dedicated DSP block, a specific RAM macro, or a clock buffer.
When would you do that?
You do that when you need precise control over the implementation, maybe for performance reasons or to guarantee the use of a specific resource. The downside is that instantiation makes your code less portable. If moved to a different chip family or vendor, that specific primitive might not exist and you'll have to change your code.
So how do people manage this? Is there a best practice?
A common approach is the wrapper pattern. You create a module that has a standard portable interface and mostly behavioral code inside. But within that wrapper, you might have conditional logic, maybe using generate statements, to instantiate a vendor-specific primitive if targeting that specific technology, otherwise falling back to a purely behavioral description. This keeps the instantiation localized and the rest of your design clean and portable.
Okay, makes sense. Wrapper pattern. Now, beyond just getting the logic right, performance is key. Making the design run fast, meeting timing requirements. How do you write RTL with timing in mind?
Yeah, timing closure is a huge part of the job. Fundamentally, it boils down to managing the amount of combinational logic between registers the logic depth. Every clock cycle, signals have a limited amount of time to propagate from the output of one flip-flop through all the combinatorial logic gates, ANDs, ORs, adders, muxes, etc., and arrive stably at the input of the next flip-flop before the next clock edge arrives.
The setup time requirement.
Exactly. If the path through the combinatorial logic is too long, takes too much delay, you get a timing violation. The signal doesn't arrive in time.
So how do you fix a path that's too long?
The most common and fundamental technique is pipelining. You strategically insert additional registers within that long combinatorial path. This breaks the single long path into two or more shorter, faster paths.
Ah, like adding pit stops in a race.
Kind of. Each segment now only needs to complete its work within one clock cycle. The trade-off is that it introduces latency. It now takes more clock cycles for the data to travel all the way through the pipeline logic. But the huge benefit is that you can run the whole system at a much higher clock frequency, higher throughput.
So more stages, more cycles, but faster overall clock.
Precisely. Think about a really complex calculation, maybe a multi-input adder or multiplier. Instead of trying to do it all in one cycle, you might pipeline it into 2, 3, or more stages. Each stage does part of the calculation. This allows the clock to run much faster.
Are there other tips for writing timing-aware RTL?
Definitely. Besides pipelining, general advice includes avoid deeply nested if or case statements in critical paths, as they can create complex multiplexer logic. Break down complex arithmetic expressions into smaller steps, and a really important one, register the inputs and outputs of your modules. This helps isolate timing paths within each module, making timing closure easier for the tools and making the modules easier to reuse.
Okay, register inputs and outputs. Got it. Got it. You've designed this amazing high-performance, functionally correct chip. It gets manufactured. How do you actually test the physical silicon chip to make sure the manufacturing process didn't introduce defects? And if it gets into the lab and doesn't work, how do you debug it?
Right? Crucial steps. That's where design for test, DFT, and design for debug, DFD, come in. These aren't features the end user sees, but they're essential additions to the hardware specifically to make testing and debugging possible. It's all about improving controllability, the ability to set internal states, and observability, the ability to see internal states.
So DFT is mainly for manufacturing tests.
Primarily, yes. The most pervasive DFT technique is scan chains. The basic idea is that, in a special test mode, all or most of the flip-flops in the design are reconfigured to connect together head to tail, forming long shift registers.
Like a giant conga line of flip-flops.
Exactly. An external tester machine can then shift arbitrary patterns into this chain to set the state of every flip-flop controllability, clock the chip once in normal functional mode, and then shift the captured results out of the chain to see what happened, observability. This allows testing for manufacturing defects like stuck-at faults, a node stuck at 0 or 1, or transition faults.
Okay, scan covers the general logic. What about regular structures like memories?
For regular structures like RAMs or ROMs, built-in self-test or BIST is common. You add extra logic on the chip itself, a pattern generator, and an output response analyzer, often using a technique called signature analysis. In test mode, the BIAS controller automatically runs test patterns on the memory and checks that the output is correct, reporting a simple pass-fail result. It avoids needing complex patterns from the external tester.
So that's DFT for manufacturing. What about DFT for debugging when things go wrong after the chip is made, like in the lab?
DFD focuses on helping engineers figure out why a chip isn't working as expected during post-silicon validation or customer returns. A common technique is to include on-chip logic analyzers. Think of something like a Xilinx ILA or Intel Signal Tap. These are dedicated debug IP blocks you instantiate in your design. They can be configured, usually via JTAG, to trigger on certain conditions and capture the values of many internal signals over time, storing them in an on-chip RAM. You can then read out the captured waveforms.
Like having an oscilloscope probe inside the chip.
Exactly. It gives you visibility into what's happening internally at full speed. Simpler DFD might just involve adding debug registers, special registers mapped into the processor's address space, or accessible via JTAG, allowing software or a debugger to read out critical internal states or status flags. And sometimes, even the DFT scan chains can be repurposed for debug, allowing you to stop the clocks and scan out the entire state of the chip at the moment a failure occurred, known as scan dump.
It sounds like you really need to plan for DFT and DFD from the start. You can't just add it later.
Absolutely crucial. The shift left mentality applies here too. Designing for testability and debuggability needs to be considered early in the design cycle. Adding scan chains or BS logic impacts area and timing, and debug access points need to be planned architecturally. Trying to retrofit it late in the game is often painful or impossible.
Okay, shifting left. Let's talk about catching problems even earlier, before simulation even. Linting tools. How important are they?
Hugely important. Think of a linter as an automated code review tool specifically for HDL. It's often the very first line of defense against common mistakes.
What kinds of things do linters check?
A wide range. They check for basic stylistic issues, naming conventions, comments, consistent indentation, which improves readability and maintainability. But more critically, they check for potential synthesizability problems, like those inferred latches we discussed, or incomplete sensitivity lists in always blocks, or multiple drivers fighting for the same signal. They also perform structural checks, like finding unused ports, unconnected logic, or mismatches in bit widths between connected signals.
So they catch common coding errors and potential synthesis issues.
Yes, but arguably the most valuable checks done by modern static analysis tools fall under CDC-RDC analysis. CDC is clock domain crossing, RDC is reset domain crossing. Specialized tools will analyze your design's clocking and reset structures, identify every signal that crosses between asynchronous domains, and check if proper synchronization logic, like those two-flop synchronizers or FIFOs, is in place.
Ah, so they automatically find those potentially dangerous unsynchronized crossings.
Exactly. Given how subtle and hard to debug metastability issues are, automated CDC-RDC checking is considered absolutely essential for any non-trivial multi-clock design today. Getting a clean report from your lint and CDC tools is usually a mandatory sign-off requirement before you even think about taping out an ASIC.
Okay, linting and static analysis are vital first steps. What about going beyond simulation? Formal verification sounds intense.
It is intense, but incredibly powerful. Unlike simulation, which only checks the design's behavior for the specific input stimulus you provide, formal verification aims to mathematically prove properties about your design's behavior for all possible input sequences.
Prove. For all inputs. How?
It uses mathematical algorithms based on logic and state space exploration. The most common type used in industry is property checking, also called model checking. Here, you write specific properties about your design's intended behavior, usually using a formal property language like System Verilog assertions, SVA, or the property specification language, PSL.
Like those SVA examples you gave earlier.
Precisely. You might assert, the FIFO full and empty signals can never be active at the same time, or every request must eventually receive a grant. The formal verification tool then takes your RTL design and the property you wrote, and it exhaustively explores all possible reachable states of the design to see if it can find any scenario, any sequence of inputs that would violate that property.
And if it finds one?
If it finds a violation, it generates a counterexample, typically a waveform showing the exact sequence of inputs and state changes that leads to the property failure. This is invaluable for debugging. If the tool cannot find a violation after exhaustively searching, it mathematically proves that the property holds true for all possible inputs and all time.
That sounds amazing for critical properties. Where is it most effective?
Formal verification really excels at finding deep corner case bugs in control-dominated logic state machines, arbiters, complex protocol logic, interface controllers, things where the state space is complex, but maybe the data paths aren't the primary concern. It's less effective generally for verifying complex data transformations, like a floating point unit, where simulation is often better. They are truly complementary technologies, simulation for data path validation and broad functional testing, formal for proving critical control properties and finding corner case bugs. A classic example where formal shines is verifying FIFO controllers, proving things like never full and empty simultaneously, or data written is never lost.
Okay, formal gives you mathematical proof for specific properties. Now, let's say you've built a really great, well-verified, parameterized HDL module, maybe an AXI interconnect or a memory controller. How do you package that up so others can easily integrate it into their larger designs, maybe even across different companies?
That's where standards like IPXCT come in. Think of IPXAC as an XML-based standard for creating an electronic data sheet or metadata file that describes your IP core. It goes alongside the actual HDL files.
What kind of information does it capture?
All sorts of things needed for integration. It describes the IP's ports and interfaces, often using standard definitions like AMBA, AXI, or APB. It details the memory maps, which address ranges correspond to which internal registers or memory regions. It lists the associated files, HDL, constraints, documentation. It defines the parameters or generics the IP uses and their allowable values.
So it's data about the data.
Exactly, metadata. The real power comes when design automation tools use this IP XACT description. Tools can automatically parse these files to connect IP blocks together correctly at the top level of an OSO, generate the necessary interconnect logic like bus fabrics, create address decoders, and even generate software header files for firmware developers, providing the register definitions and addresses. It enables much more efficient IP integration and reuse.
So if you're building a library of reusable IP components for your team or company, using something like IPXACT is key.
Absolutely. Building a truly reusable IP library requires more than just writing good HDL. It demands a product-oriented mindset. Each IP core needs a clear specification. It should be designed for reuse from the start with good parameterization. It needs comprehensive documentation, a rigorous self-contained verification environment, maybe using UVM. It should follow standardized coding styles, be under robust version control, and have clear ownership for ongoing maintenance and support. IPXACT helps manage the metadata aspect of that.
Okay, that makes sense for managing today's complexity. What about the future? Where are HDLs heading? Are we moving beyond just writing RTL?
That's a fascinating question. We are definitely seeing the rise of what are sometimes called hardware construction languages, or HCLs. Examples include Chisel, which is based on Scala, and Spinal HDL, also Scala-based.
Hardware construction languages, how are they different from HDLs?
They represent a higher level of abstraction. They aren't HDLs in the traditional sense of directly describing hardware structures like Verilog or VHDL do. Instead, they are domain-specific languages, DSLs, embedded within powerful general-purpose programming languages like Scala. Using the features of Scala, like its strong type system, functional programming capabilities, and object-oriented features, designers write programs that generate Verilog RTL code.
So you write Scala code that writes Verilog code.
Essentially, yes, you're writing generators. This allows for incredibly powerful parameterization and abstraction. Imagine writing a single chisel generator that can produce an entire family of RISC-V processors, different pipeline depths, different cache configurations, optional extensions, all from one configurable generator codebase. It leverages software engineering principles to build hardware generators.
That sounds like a huge productivity boost for creating complex, configurable hardware. What are the challenges or trade-offs?
There are definitely trade-offs. One major challenge is the readability and debuggability of the generated RTL. It's machine-generated code, often not intended for direct human consumption, so figuring out why the generated Verilog doesn't work can sometimes be difficult.
Right, you're debugging the generator, not the output directly.
Exactly. Another challenge is that the verification ecosystem around these HCLs, while evolving, is generally less mature than the massive infrastructure built up around Verilog, System Verilog, and UVM, especially for verifying the generated RTL. And, of course, there's a learning curve. Engineers need to learn Scala and the specific HCL framework, which is different from traditional HDL design.
So it's a powerful paradigm shift,
Yeah.
but still facing adoption hurdles. It raises that interesting question. Will hardware design become fully automated eventually? Or will engineers always need to understand the low-level RTL details?
That's the million-dollar question, isn't it? The trend is definitely towards higher abstraction.
We've covered a massive amount of ground today, a real deep dive into this world of hardware description languages, from Verilog and VHDL's origins right up to these modern construction languages and verification methods.
Yeah, it's quite a journey, and looking at the big picture, it's clear there's no single winner language. It really is about having a toolbox and choosing the right tool for the job.
So for huge, complex ASICs,
System Verilog, combined with UVM for verification, is undeniably the dominant standard. The ecosystem, the tool support, the available talent pool, it's all geared towards that for large-scale digital design and verification.
but VHDL still has its place.
Absolutely. For high-reliability applications, or in many FPGA design flows where its rigor and strong typing are valued, VHDL remains a very powerful and widely used language for RTL design.
And HLS.
HLS is a game changer for designs that are algorithm-heavy, signal processing, machine learning accelerators. areas where you can express the core logic more naturally in C++ or System C, but remembering that hardware-aware coding style is key to getting good results.
It really highlights how much the field has evolved. We've gone from just trying to describe hardware functionality with early Verilog and VHDL to needing these incredibly sophisticated methods like UVM and formal verification just to prove our complex designs are correct. That jump from basic reg types to full object-oriented test benches, it's enormous.
It reflects the relentless pace of Moore's law and the complexity it enabled. The modern hardware engineer can't just be an expert coder anymore. They have to be a system architect, understanding these trade-offs between languages, verification methodologies, power, timing, testability, strategically applying the right techniques to deliver working silicon in this era of just mind-boggling complexity.
Which brings us to our final thought for you, the listener. Given this constant push for higher levels of abstraction from schematics to HDLs to HLS to hardware construction languages, what fundamental hardware concepts do you think will always remain essential for an engineer to truly understand deep down, even as the design tools become ever more powerful and automated? Something to ponder.